All right, let's try and use this iPad as sort of a whiteboard to help walk you through some of the questions here. So, or some of the topics, let's say. So I know so far you've done some statics, right? So that was sum of all forces equals 0. And what we're going to do now is we're going to get into some dynamics. How is our body producing dynamic motion? And here, if you remember from Newton's second law, right, so if we have Newton's second law states that the sum of forces actually equals mass times acceleration. So the statics one is also Newton's second law too, I guess, right? It's just basically that, like, there is no acceleration. So in this case, right, this is 0 because this is mass times 0 because it's not moving. So again, it's the same law, just a simplified approach. When something starts to move, we need to start thinking more about what's happening with the motion or what's happening with the acceleration. And to do this, let's use deadlifting as our example. So let's start thinking about how would we deadlift, right? If we wanted to move an object off the ground, how are you going to do that? So let me draw a little barbell here. Sorry for my art skills, right? So if the bar's just sitting here, what sort of forces are going to be acting on the bar, right? So it's sitting there on the platform waiting for you to go rip it off the ground. What are the forces acting on it? Well, you have weight, right? So we have the force from weight, force due to gravity. And when it's sitting there, we actually also have these normal forces, right? So we can call it N1 and N2, and that's just the ground pushing back up on the bar, right? Because the weight has to be balanced with the force on the ground, otherwise the weight would be going through the ground, right? So at that instant, it's in static equilibrium. And then what you're going to do is you're going to go up to it, right? You're going to grab hold of that sucker, and you're going to apply a force in the upper direction, the force from the pole. Right? So if we wanted to look at, well, let's look at Newton's second law, right? We can say, well, we have, again, the sum of our forces equals mass times acceleration. And also, you might not have seen this before, but these underlines here, right? So that underline just means it's a vector. You may have seen over bars before, right? Under bars are basically the same thing. It's just the convention that the text I teach out of uses, right? So that's, the underline means it's a vector. And we need to sort of think about, well, what does that mean? What does a vector mean? Well, vectors give you two pieces of information. One, the magnitude, right? And also the direction. So here, let's only consider the y direction, with y being positive upward. So that way all the forces are either going to be in positive or negative y, so we don't need to worry too much about the direction, so we can get rid of the vector approach. Right? So if we're just looking in the y direction, well, what are the forces acting on this, right? So left-hand side, the sum of all the forces. Well, one, we have the force of the pole, right? And then we have minus the force of the weight. We have plus N1 plus N2. All of that equals mass times the acceleration in the y direction, just like that. All right. So when we're thinking about this, what happens as soon as your force of the pull equals force of the weight? Right? So at that instant, when right before the bar starts to move, right? Because if you think about it, if we're just pulling with very little force, the bar isn't actually going to accelerate, right? It's still going to be static. But once, right? Once F pull is greater than or equal to the weight on the bar, right? Then our N1 and N2 immediately go to 0, right? The ground can't push up back on the force of the weight if it's not touching. The ground can't push on the bar or the plates if it's not touching the ground, right? That makes sense. So when F pull is less than F weight, there's some varying amount of N1 and N2, but let's just think about it from this point forward. as soon as that bar just before it starts to move, where n1 and n2 equal 0. Okay? So what are some of the ideas of the kinematics of motion, right? So this idea of kinematics, so dynamics is two things, right? You can think of dynamics has two components. One is kinetics, right? So I don't know if you've heard of like the kinetic response or military kinetics, right? That's the force. That's the force side. So the kinetics is this side of the equation, right? That's the kinetics. And then the other part is kinematics, which kinematics is the geometry of motion. So that's the motion part, or the MAY part, basically the AY part. So if we think about kinematics, right, what are some things we want to measure when we're looking at kinematics? So for kinematics, the things we like to think about, or we need to think about, are position, right? Where is an object in space? What's the position? Do we know what its velocity is? And lastly, do we know the acceleration? Okay. Position, if we're looking at just the vertical direction, we'll often denote that as just y, right? Velocity, we can say that's y dot, and then acceleration is y double dot, right? And in this scenario, the convention usually is that dot means the derivative with respect to time. So if we take this, right, and we have position, if you have something's position and you want its velocity, you can take the derivative with respect to time of that position and you'll get velocity. Same thing here. If you take the derivative of velocity, or the second derivative of position, then you'll get acceleration. On the other side of that, right, if you have acceleration and you want velocity, well, what do you got to do? You have to integrate it from t1 to t2, right? The integral is the opposite of derivative. Again, we can integrate it one more time from some time 1 to time 2. So this is our integrate side. And the other side going downward is our derivative side. So these are inherently related, right? Position, velocity, and acceleration are inherently related, where velocity is the change in position over time, acceleration is change in velocity over time. They are related to each other, right? And over here, for our Newton's second law, well, what is acceleration, right? Our acceleration, let me get a different color, maybe black, right? This is right here. So our AY in this case is just y double dot. So if we want to know how is something accelerating, right? How is it going to accelerate? What we need to know is, well, what's the difference between force of the pull and force of the weight, right? If we know what the difference is between those two forces, then that difference is going to be proportional to our mass of the object times that y double dot, or the acceleration. All right. So if that's our sort of Newton's second law approach, really what you need to also know is these other terms of impulse and momentum. So what is impulse and momentum? And interestingly enough, when Newton was thinking up and came up with Newton's second law, he was really thinking about it in terms of momentum. So what is momentum? If you want to mathematically describe momentum, it's going to be mass times a velocity, right? And this mass times a velocity is really just mass in motion. So if you have mass in motion, or an object has mass in motion, it has momentum, right? And the amount of momentum it has is the mass times the velocity, and it has a direction associated with it, okay? So if you want to change something's momentum, right, you can apply a force, but you actually have to apply a force over some amount of time, right? You can't just apply it for a split second. If you really want something to change its velocity, you need to apply a force, but that force needs to be over some amount of time. So this impulse term is the integral of force dt from some time 1 to some time 2. And then we can change this side of the equation to v2 minus mv1, right? So if we have something, an object or a system, and we want to change its velocity to some velocity 2 from some velocity 1, we need to apply this impulse to the object. And we can plot impulse just to give you a better sense of what sort of an integral is, in case you're a little bit rusty, right? So if we have force on the y-axis and we have time on the x-axis, let's say at time 1, I'm applying no force, 0 force. At some time 2, right, I'm applying some other force right there, right? And then let's say at this time 2, I immediately stop applying force, right? So you're like, well, how much force did you apply? Well, it depends, right? I applied this much force at this instant, then this much, then this much, then this much, then I hit my max, and then I applied 0. So how does that change velocity? Well, what you need to look at is what's the area under this curve, right? What is the integral of force over time? And that is what changes our momentum. And if you think about what we just talked about too, well, what's the derivative of velocity? So let's say we want to take the derivative here. So let's take this equation and let's take the derivative with respect to time. So what's the derivative of mass with respect to time? Mass stays the same with time, let's say in this problem. What's the change in velocity from v2 to v1? Well, that's acceleration, right? Here we go. If we want to look at how does velocity change, velocity changes with time. Now we have acceleration. And if we take the derivative of an integral, right? We have this integral here, we take the derivative of that, then we're just left with force, right? So this is how you sort of get Newton's second law from how he was thinking about it with impulse and momentum. All right. So I think that's fairly clear, right? And again, if acceleration equals 0, we're just right back up to the top here where now we're talking statics. So you've done some statics before, you've done some acceleration equals 0 stuff. But now if we're looking at forces, how fast is it going to move, right? When somebody says how fast is it going to move, well, what are you talking about? Are you talking about how fast is its velocity going to change, or how fast is its position going to change, or how, really quantifying and being sure about what you're trying to look at, its velocity or its acceleration or its position, is important to know what's related to that specific quantity, because it's not always just force. All right, the last-ish thing I want to talk about is power. So this idea of power. So what is the equation for power? So power is actually equal to force times velocity. Right? So if we have the force we're applying to an object and we have the velocity, then we can calculate the power. Right? So you think if we have a very large force, right? So if we have a really big force, but we have no velocity, we have no power, right? Then we're just applying a force, but we don't actually have any power. If we have a ton of velocity, if we're moving something really fast, but we're not applying a ton of force to the object or the system, again, then we have very little power. So how does your body or your muscles generate power? Well, for one, we got to kind of talk about first, how do your muscles generate force? So how do muscles generate force? All right, well, Major Feltner told me to talk to you about this, so you should know, but we'll review it anyway, right? How do muscles generate force? Well, there's like physical things happening inside of your muscles, right? You have these actin and myosin cross bridges, right? So these little myosin heads are like grabbing onto the actin portion of your muscle fibers, right? These two things are developing cross bridges, and they're pulling the two sides of your muscles closer together. So if you have an attachment and an origin of your muscle on two different bones, right? It's going to pull those 2 points closer together, and that's what makes the motion of your bones, right? Those muscles have physical things that are grabbing, latching on, letting go, grabbing and latching on again to shorten over time. And all of these, right? This sort of makes up the workhorse or the singular unit of a muscle, which is a sarcomere. All right, so we have this sarcomere, right? And you have tons and tons of these sarcomeres in series and in parallel, and they're all shortening and grabbing and pulling, right? But there are some limitations to that force that it generates. So if we think about, well, let's look at another little plot here. So we have on the y-axis, we're going to look at force, and on the x-axis, we're going to look at velocity. So here we're going to have force. So this is our force velocity curve for a muscle. Okay. So here's our force velocity curve. So at 0 velocity, we're going to call that our isometric contraction. I think you've talked about that too, right? That's a static contraction. Your muscles are generating force, but they are not actually contracting. They're not moving. It's just holding still. And then on this side, we're going to have our concentric contraction. So that's where we're generating force and our muscles are moving, are shortening. They're actively shortening. And then over here, what we're going to talk about is our eccentric contraction, where the muscles, again, they can provide force, but they are actively lengthening. All right. So let's plot a little bit of this. So let's say here, this is the amount of force, let's just call it F naught. All right, F naught that you can generate with an isometric contraction. So can you generate more force or less force as you start to work this way, concentrically? What do you think? Well, let's think about some velocity. If I gave you something in your hand, right, that's very light, there's some maximal speed that you can generate force against that object, right? There's some max. But what about if I told you to move it faster? Right, if I'm like, well, move this pencil faster, generate more force to move it faster, could you do it? Right? There's some point where we can only move at some max speed. So this is our max contraction velocity. And above this speed, if you try to go over here, your muscles just can't move any faster, so they can't generate any force at that speed. Does that make sense? Right? So if there's some max here, right, there's some relationship. I'm going to make it real simple and just draw a straight line. I know it's in real life not a perfectly straight line, right, but it's something like that, where as you try and move faster and faster, your muscles cannot generate as much force. And the reason is, it comes back to, right, these physical systems, these cross bridges, they can only move so fast. When they're trying to move fast, they're not going to be able to grab on as quickly. You might miss some grabbing on between them, right? There's just limitations. So now for the eccentric side, actually your muscles can generate more force eccentrically than they can concentrically or even isometrically, right? So you can actually generate a higher amount of force as your muscle is lengthening. That's sort of like a negative, right? So you can imagine you can definitely do negatives with more weight than you can concentric contractions in the weight room, but also realize that you're messing with the acceleration there too, and the acceleration due to gravity. So that it's not purely due to the eccentric contraction. It also has to do with the dynamics of the motion and the acceleration terms we've talked about earlier. All right, so if that's how our muscle generates force, right, then we were trying to figure out power, right? So if we want to get power, well, now we know how they generate force and velocity, and guess what? That's what we need to figure out muscle powers, force and velocity. We need to multiply them together. So you can take this sort of curve and multiply it together to get a sense of power. Right? So how do we calculate power? We can look at a power curve based on those force velocity measurements. So again, draw another little graph here. Ooh. My apologies if the lines aren't straight. I'm trying to let my app do the work. Right? So if we have now power on the y-axis and velocity on the x-axis, let's use, what color do we want to use? Let's use something weird. This one. Right? So how much power are you generating when you're applying a ton of force, right? Power is force dotted with velocity, right? So you have a ton of force, but you have zero velocity. This is zero velocity. How much power can you generate? Well, none, because you have no force. Sorry, you have a ton of force, but you have no velocity. What about here? There's some point, right, where if we get above this value, we can't generate any force. So at that point, force equals 0, even though velocity is high. So again, we're at 0. So what does this curve look like in between? right? Where 0 at the left side, 0 on the right, there's going to be some curve like that, right? And here, at this point in time, this would be the velocity where you can generate your max power. Right? And just to also be clear, this whole time, this is all sort of your max. So this is the maximum power you can generate at each of these given velocities, right? So at this velocity, at this velocity, at this velocity, at this velocity. It's all the max power at each of those velocities, but there is like a single point where you can have the most power overall at that specific velocity, and that could be your max power velocity. Okay? So again, our power equals force times velocity. Another way to think about it, so this is power, right? Another thing you might have heard of before is it's, from the angular sense, it's torque times angular velocity. Again, both of these are vectors, right? For your car, you've probably thought, if you have a car, or you've thought about cars before, your car has some amount of torque, but that's not exactly equivalent to the amount of power it has, right? The horsepower. So you can have torque, you have to multiply that by the angular velocity at which you can generate that torque. So you end up with this sort of power band. And this power band here is also interesting into, like, if you think about cycling, right? If you're riding your bicycle, you don't want the gears to be such that you can barely move the pedals, but you also don't want the gears to be such that it's super easy to move the pedals, right? If you want to go as fast as you can and put as much power into your bicycle human system, you want to set the gear ratio so it's like around here, right? So you're getting the most sort of power bang for your buck, where you're not spinning the pedals too fast, you're taking advantage of the force velocity curve of your muscles by using the gear ratios. All right, I think that's the end of what I wanted to talk about here. So now you can go back to PowerPoint and we'll finish up the lecture there.